All right, Algebra 1A students, welcome to part 1 of lesson 6.4, where we're going to be talking about real-world applications of systems of linear equations. There are many useful real-world applications of what we've been talking about in our past few lessons. The first thing that we're going to look at as an application of systems of linear equations is something called the break-even point. When businesses are making things and selling things, they always lose money at the start because they have to buy materials, they have to buy space to create whatever they're selling, and then as they sell things, they make that money back until a certain point when they start to make money on their business. So what we do is we represent costs and revenues with two equations, and we see where those two equations would intersect, which means the solution to that system. So for example, if we look at this problem here, it says a fashion designer makes and sells hats. The material for each hat costs $5.50. The hats sell for $12.50 each, and the designer spends $1,400 on advertising. To start with, how many hats must the designer sell to then break even on that cost of his advertising? So what I do is I create two equations. One of them is an equation for the cost of the hats. And the total cost, which I'll represent with my y variable, is equal to 5.50 times x, which is the number of hats that I'm making or selling. So this equation here is an equation for the cost of this fashion designer's business. Right? And then of course I also have an equation for the money that I make. Not only the money I have to spend to make the hats, but also the money I make when I sell the hats. And I'm told that the hats sell for $12.50 each, so I do y equals 12.5 times x. Now the additional piece of information they told me is the designer also has to spend, remember this is my spending equation here, spending and my money that I'm making. So I'm also told that I am spending $1,400 on advertising. So in addition to the $550 for the materials of each hat, I'm spending $1,400 on advertising as well. Now this is an equation that we should be able to solve. It's one that I would solve with substitution because I already know what the y is equal to. So hopefully we remember substitution and we can see that y in this case is equal to 12.5x, and I can put that into that equation over there, and the new equation I get is 12.50x equals 5.50x plus 1,400. So this equation is what I get based on my substitution, and then I can solve this for x by minusing 550x. Get rid of that. Minus it over here as well. Oops, minus 550x. And of course I get 7x when I minus those. The other side of the equation is now just 1,400. And if I divide by 7 and divide by 7, I get that x is equal to 200. If I plug that back in to maybe this equation over here, I can pretty quickly get that y is equal to, well, whatever 12.5 times 200 is, right? And that would be 2,500. $2,500. So at the point when I have made and sold 200 hats, I have spent $2,500 on my advertising and my materials, and I've also made $2,500 on the hats that I'm selling. So remember, the question here is asking how many hats must the designer sell to break even? Well, that's this guy right over here. because remember my x was the number of hats. So all I care about is that x is 200. Of course, you could also find the y value, but that's not really what we're talking about. Here we're talking about how many hats do we have to sell to break even. So these break-even kind of problems are one way that we can apply linear systems of equations, or systems of equations that we've been dealing with. The other thing that we need to be aware of is that when we go into a real-world situation, sometimes the numbers that we arrive at based on our algebra skills don't make any sense in the context of what we were talking about. So in real-world situations, you have to consider the constraints. You have to consider the constraints in the problem, okay? So if we look at this particular example, it says a local zoo is filling 2 water tanks for the elephant exhibit. One water tank has 50 gallons of water, 50 gallons, and it's being filled or added to at a constant rate of 10 gallons per hour. Well, per hour means times hours, which I'll use a variable for. That's the total amount of water in that tank, right? So the water is equal to 50 gallons plus 10 gallons per hour. Okay. The other tank in the elephant cage is currently holding 29 gallons of water, and that one's being being filled by a smaller hose that's only getting 3 gallons per hour, right? So again, I have a system of equations here. It's another one that I'm probably going to solve with substitution, because I know that W is equal to all of this, 29 plus 3H, so I can put that up in there, and I get this equation, 29 plus 3H is equal to 50 plus 10H. And now this is an equation that I'm going to try to solve for H. First thing I'm going to do is minus my 3H's so that they're all on the same side. I think I get 7H then on that side. And then I'll minus the 50 to get that over to the side with the 29. 29 take away 50, I end up at negative 21 is equal to 7H. And if I divide by 7, I get that H is equal to negative 3. Right? H is equal to negative 3. And if I plug that back into one of my equations, I get that the amount of water that I had in them at that time is 20 gallons. Okay, so what we have to understand then about this as our solution, when will the 2 tanks have the same amount of water? Well, negative 3 hours from now. But getting negative 3 hours doesn't really make any sense. Sort of an illogical answer, right? How can we have the same amount of water 3 hours ago when we just started filling them up? That doesn't really make any sense. It also doesn't make sense that both tanks would then have 20 gallons in it, because one of them started with 50 and the other started with 29. So how can I fill them up and end up at 20 gallons? It just doesn't make any sense. So this as a solution doesn't make any sense. It's not a viable solution. So what we would say is never, right? When will the 2 tanks have the same amount of water? Never. They'll never have the same amount of water, because my solution of negative 3 hours doesn't make any sense. Okay? So make sure that we're on the lookout for something like this, where the answer that we arrive at is totally illogical, and there's no way that that could have been the answer. If you have questions about applications of linear systems, applications of systems of equations, please make a note to ask me in class tomorrow. Hardest part about this, in my opinion, is writing the equations, because once we get that, it's just like what we've been doing for a long time. So if you have questions, please make a note to ask me in class tomorrow. Otherwise, that's all I have for you. Have a wonderful night.